So hi everyone. So far we have discussed a wide variety of op-amp based circuits, and we analyzed them. We discussed different techniques to analyze op-amp based circuits. So here I've summarized all the wide range of circuits that you would encounter that you have encountered so far. So the first one here is an inverting amplifier. The second one is a non-inverting amplifier. The third one is a simple voltage follower. The fourth one is a trans impedance amplifier, which converts currents to voltage outputs, current inputs to voltage outputs. Then, so again, if you see, all these guys are the first, the amplifiers which I've shown here. These are all, they just manipulate an input. I can treat them like amplifiers with a finite gain, right? They are all amplifiers with some kind of gain. If you count this guy also as an amplifier, it's a trans impedance amplifier. They are all kind of some forms of amplifiers. The second row, these two circuits, they are adders and subtraction. They can add two voltages and subtract two voltages. So this is an inverting adder. We also discussed circuit for a non-inverting adder, but I'm not showing that because this is more commonly used. An inverting adder. This circuit is a voltage subtractor. It can subtract two voltages. We will later see circuits where these are used. You will see that this concept of adding voltages is used in multiple applications. One very famous application is in analog to digital converters. So once we discuss those topics, at that time I'll talk about it. But this is one application of that. Then the other two applications, where op-amps are used for performing interesting math operations, is integration and differentiation. So these two circuits are both inverting integrators and differentiators. Okay, where the output voltage is integral of or derivative of the input voltage. Then we also discussed the circuit for a non-inverting integrator, which you can build using a single op-amp. So here, if you see, this is an inverting integrator. So to achieve non-inverting integrator, you'll have to put an additional op-amp with a gain of -1. Okay, you'll have to flip it once again. And similarly, for an non-inverting differentiator, you'll have to put an additional gain of -1. But without doing that, we just exploited the property that we discussed in the previous lecture, that using an op-amp, you can realize inverse of transfer functions. Using this property, we could actually realize non-inverting integrators and differentiators using just a single op-amp. So that's what I've showed here. This is a non-inverting differentiator, and this one is a non-inverting integrator. So I've just not drawn the circuit fully here for non-inverting differentiator. Okay, there should be a cap and a resistor here, and the input signal should be applied at this point. And we also discussed another circuit, which is a low-pass filter with a finite gain. So it's an active circuit. So it can give you a low-pass filter, which is a first-order low-pass filter transfer function with a gain that you can vary. So these are the wide range of circuits that we have discussed so far. Now, hopefully, this should equip you with the skills to analyze any op-amp based circuit. So what we'll do now is analyze a range of op-amp based circuits, which mainly test your understanding of the functioning of an op-amp. So we'll start with the first circuit. Shown here is a feedback based op-amp circuit. So can you tell me what will be the output voltage in terms of Vi? Use the rules that we have discussed so far. Okay, you don't have to keep writing KCLs and KVLs. Just try to see some patterns and try to use some rules. Is this first question, whenever you are given an op-amp circuit in feedback, just check, is it in negative feedback or not? Is this circuit in negative feedback? So first step, identify this. What is this amplifier? What kind of an amplifier is that? You're applying input to It's a non-inverting amplifier, right? What is the gain of this non-inverting amplifier? 2, right? The gain of this non-inverting amplifier is just 2. 1 plus R2 by R1, R and R are same, so it's just 2. So now you have a situation like this. You have a forward path amplifier with a gain of infinity and a feedback path gain of 2. So now tell me what will be the closed loop gain for this circuit. Closed loop gain for the circuit. 1 by 2, right? 1 by beta, because the forward path gain is infinity. This op amp is still in negative feedback. So the closed loop gain is 1 by beta. Beta here is 2. So normally we are used to beta being less than 1. I took an example where beta is greater than 1. So the closed loop gain will be half. It will be less than 1. Okay. Now look at this circuit. So is this circuit in negative feedback? The first step, you'll have to question yourself, is this circuit in negative feedback or not? Output is fed to a circuit like this here. This circuit, if you just take this circuit alone, what is this circuit doing? Do you recall? Does it resemble any other circuit that we have discussed so far? An RC section and fed to a non-inverting op-amp, a non-inverting op-amp configuration with a cap in the feedback path. What circuit does it remind you of? You can use the cheat sheet. I mean, you have the sheet with you. This is a non-inverting integrator. Okay, this circuit is a non-inverting integrator with a transfer function of 1 by SRC. So I have this whole transfer function is just 1 by SRC. So now tell me what will be your closed loop gain for the circuit. The feedback path is 1 by SRC. So what will be the closed loop gain for the circuit? SRC. That's it. It's just 1 by beta. So the closed loop gain, V naught by Vi of S, is 1 by beta, which is simply SRC. So see, I have built a differentiator using an integrator. So if I put a differentiator in the feedback path and an infinite gain in the forward path, then I can get a differentiator. So if I put an integrator in the feedback path and an infinite gain in the forward path, then I get a differentiator in the closed loop. I can get a differentiator. The opposite holds true. If I put a differentiator in the forward path, in the feedback path, I would get an integrator. I'll get 1 by SRC. It's simply 1 by beta of S. I'm just testing that idea here. The circuit looks complex. A quick inspection of the circuit should reveal you that it is in negative feedback. Why is it in negative feedback? This circuit alone, on a standalone, is a non-inverting configuration. From this point to this point, it is positive. Then there is a negative sign here. So there is a phase inversion. From when you go from here to here, there is a phase inversion. That's it. The circuit is in negative feedback. Right now, don't worry about stability. It's a single pole system. So you don't have to worry about it. So yeah, you're fine. So this circuit is fine. And the forward path gain is infinity. So the transfer function will simply be 1 by beta of S. This circuit, I just told you guys, you can look at your the cheat sheet that we have had. And it's a inverting integrator. So this. Yeah. This is a transfer. Yeah, this is exactly a transfer function inverter using feedback. Yes. Okay. So now we'll then quickly analyze problems based on. So here I've removed the frequency dependence now. These questions, the ideas behind these questions we discussed in the previous lecture. So you should be able to solve all of them using just the basic ideas. So here you're given a op amp circuit and you're supposed to find out the output voltage and the output current that the op-amp is supplying. Fine. So now try analyzing the circuit and try arriving at the voltage value V0 and also what is the value of the current I0. So step one, when you are given an op-amp circuit, just look. First step, you have to see, is this op-amp at negative feedback? Is this a negative feedback or not? Yes, right. This circuit is a negative feedback. If the op-amp is a negative feedback, what is this node voltage? 0. V plus will be equal to V minus, which is in this case 0. So if this is at 0 volts, what is the current flowing through this resistor? 0. No current flows through it because on both the sides of the resistor is at 0 volts. So if this current is 0, where do you think this IB has to flow? IB cannot flow here. It cannot go inside the op-amp because the input current into the op-amp is 0. The only path that IB can take is through this resistor. Therefore, the voltage drop across the resistor will be IBR. And the current IB has to flow into the op-amp. So the value of I0, the current, since I've shown the current in this direction, I0 equals minus IB. And what will be the voltage V0? IB times R, minus IB times R. That's right. So because your current is flowing in this direction, it's minus IB times R. So your V0 is minus IB times R. I0 here is just minus IB. Okay. So if you have any questions, you can just ask me in this one. I'll move on to the next problem if you don't have anything. Okay. So use the same principles that I've discussed so far. You are given this op-amp circuit. Step one, start with negative feedback or not. Apply the virtual ground concepts and then try to solve it. Try solving it yourself and tell me what should be I0 and V0. So step one, is it in negative or positive feedback? Just you should check that first. So what's V0? What is the voltage V0 for the circuit? So look at it this way. Is this circuit in negative feedback? Yes, it is a negative feedback, right? Because the output terminal is connected to the inverting terminal. If the circuit is a negative feedback, then immediately V plus, the inverting and non-inverting terminals will follow each other. So it's a virtual short. So this node will be at 0. If this node is 0, then the current through the resistor is 0. If the current through the resistor is 0, then I can just remove there is no current. There is no current flowing here. Since no current flows into the op-amp, what should be the current through this resistor? The current flowing here is 0. This current is therefore, this current also has to be 0. There is no path for the current. Therefore, what will be the voltage drop across the resistor? 0 volts. The voltage drop across the resistor is 0. So if this is at 0, voltage drop across the resistor is 0, then the output voltage will also be at 0 volts. And what happens to the current IB? Because it cannot, this current is 0, the entire IB flows into the op-amp. Op-amp acts like a 0-volt DC source. The output of the op-amp acts like a 0-volt DC source and it will absorb all this current. It will sink all the current. So your I0, because the direction of current, I've shown it in this way. I've shown it going outside the op-amp. I0 will be equal to minus IB. In this case, op-amp is sinking the current. Okay. I've shown I naught as a sourcing current. So I naught will be minus of IB. Okay. Next circuit. Now again, start with the circuit. Now I have put two current sources. Now this circuit is based on a very interesting idea that I learned from one of my friends. Long time. This was my student days. So see what happens to this circuit. So, and right now you're just analyzing it. So it is actually used. It's an idea that is used in building a very interesting ADC, analog to digital converter circuit. But yeah, see what happens. So first step, at the moment you have this is this op amp in feedback, negative feedback? See, current sources don't have any impact. You can treat current sources as infinite output impedances. So, I mean, two terminal devices with infinite incremental resistances. So you can ignore them when you're doing feedback analysis. So you're right. So one of you said I naught is 0. That's right. So yes, this is a negative feedback. So if this is 0, this node will also be at 0. If this node is at 0, I flows through this, then the same current has to flow through. You're right. So some of you wrote V naught equals IBR. You're right. I'll explain that. Now this current IB has to flow through the resistor because current flowing into the op amp is 0. So this current is IB. So the voltage drop across the resistor will be IB times R. And that's the output voltage. The output voltage is simply equal to IB times R. But now if you see at this node, IB current is flowing in this direction. IB current is entering this node. So no current flows through this. The current here is 0. No current flows through this. All the current that's flowing through the resistor is being supplied by this current source. This guy is supplying all the current. So this is the path for the current. So the current flows somewhere like this. So it starts here, flows here to the ground. No current flows through the op amp. So I naught equals 0, V naught equals IB times R for this circuit. Now this one, it's very similar with some small changes. Use those ideas that we have discussed so far. Again, the circuit is a negative feedback. So this is at 0 volts. This will also be at 0. Now IB's direction is opposite. It's flowing in this direction. So it has to flow into the resistor. So it will create a voltage drop of IB times R here. Yes. So this current is IB. The current entering this node from this current source is IB. So the total current entering the op amp here will be 2 IB. And that current has to flow. It has to be, it will flow into the op amp. So your I naught equals minus 2 IB. And V naught, what is the value of V naught? What is the value of V naught in this circuit? Is it plus or minus IBR? See, this node current is flowing in this direction. Okay, so this node voltage is at a higher potential than this. So V naught is at a lower potential. So V naught will be minus of IB times R. Okay, so that's the circuit. This one is a little bit interesting. It talks about a very interesting principle I wanted to discuss is assume that this op amp here is a circuit with some kind of a saturating nonlinearity. Okay, or you can ignore saturating nonlinearity condition. So this is the circuit given to you. So first step, the first question I need to ask is this op amp, assume that op amp has a saturating nonlinear characteristic, meaning your op amp characteristic should look like this. If your differential input is greater than 0, it goes to plus VSAT. Less than 0, it goes to minus VSAT. This is the characteristics of the op-amp. Now, can you tell me what will be the output voltage and the current I0? So step one, first question, is this circuit in negative feedback or not? Is it in negative feedback? No, ask yourself. So let me ask you a question like this. I have a current source and I'm pushing a current through the resistor. Let this node be Vx or some Vy. I change this node voltage by delta Y, delta Vy. What will be the change of this node? It's a current source. Keep that in mind and tell me what will be the change of this node. Let's call this IB. No change, right? Because the change here will be 0. So if I'm changing something here, no change happens here. So what is the voltage gain from this node to this node? What is the voltage gain? If I were to apply a small signal voltage at this point, what is the voltage gain here from this node to this node? What is the voltage gain? How do you measure voltage gain? Let's call this node as some Z, delta Vz upon delta Vy. Delta Vy is finite. Even if I apply a finite delta V, there is no change in delta Vz. So it is 0. The voltage gain from this node to this node is 0. Okay. So now keep this in mind and come back to this circuit. Do you think there is any feedback in the circuit? I'm changing, even if I change this output node voltage, there is no feedback because, see, when you say there is a feedback action, when your output is changing, this node should also change. But because it's a current source, no matter what you do to this node voltage, it is always going to supply a constant current. And that's not changing. Therefore, the circuit is not in negative feedback. It is being fed back to the node, but there is no, the circuit is not, because the loop gain is in 0. I mean, the current is not changing at all. So this node voltage will not, V plus will not be equal to V minus. So this current IB, it has to flow through the resistor because there is no other path. It cannot flow into the op-amp because current is 0. It will flow. So your V minus, or let's call that node as Vx, V subscript x equals V minus, what will be that voltage? V minus IB times R, right? IB flows through the resistor. It will be IB times R. Now your V minus equals IB times R. V plus equals 0. What should be V naught? What should be V naught? Your V minus is greater than V plus. So what should be V naught? Use the saturating nonlinearity characteristics, minus VSAT. So the circuit will just come to minus VSAT. It's an open loop and it will come to open loop minus VSAT and stay there. So that's the problem with the circuit. Okay, there is no feedback. It's a current source. I've connected from positive to the output to the input terminal, but there is no feedback. I'll just end this lecture with one other circuit. Okay, I just wanted to show that idea alone because it illustrates the concept of virtual ground. So I want you to find out what is the value of V naught and I naught in this circuit. The circuit looks something like this. Okay. What is the value of V naught? First, let's ignore this part, then we'll add this part. So I'm giving you a circuit like this. What will be the voltage V naught and I naught, you can express them in terms of Vi and R. What will that be? So step one, is this circuit in negative feedback? Yes, it is in negative feedback. So which means this node will be at 0 volts. If this node is at 0, will this resistance matter at all? Yes. So this resistance will not matter at all because if this node is at, the other node is also at 0, I might as well remove this resistor altogether. So even if I put a resistor here, this doesn't really matter. So Vi by R will be the current through this, and that has to flow through this. So you will get V naught becoming equal to minus Vi. Okay, that follows from it's just a inverting amplifier. And this current Vi by R is flowing in this direction through the resistor. That has to flow into the op-amp. So your I naught equals minus of Vi by R. Let's say I just add a resistor at this point, a resistor of value R. What do you think will happen to V naught and I naught? No. No change in V naught S, but will there be a change in I naught? See, the moment I add a resistor, the resistor is going to carry some current. What is the current flowing through the resistor? The current flowing through the resistor is V naught by R. And since V naught is R is minus Vi by R, so I can, if I show the direction of current, a current of value minus Vi by R is flowing in this direction. Or I can reverse the polarity of the current. I can say a current of value plus Vi by R is flowing in this direction. So now look at this node. A current of Vi by R is entering here, and there is another current Vi by R is entering here. So the total current that's flowing into the op-amp, I naught, equals minus 2 Vi by R. The moment you connect a resistor at the output, voltage remains the same, but current changes. Right? That extra current is supplied by the op-amp. So these ideas will be very useful when you're actually building op-amps. Okay, so that will be useful in determining how much current, bias currents you have to set in your op-amp and all that. Okay, I'll just add one resistor here. Let me add a resistor, and let's call this as plus VDD R. Now ignore this resistor. For this problem, we can ignore the resistor here. Now can you tell me what will be I naught and V naught? Sorry. Yeah. So now what will be I naught and V naught? So circuit is a negative feedback. This node will be at 0 volts. If this node is at 0, no current flows through this resistor. So I can ignore this resistor. So you have a current Vi by R flowing through this. And the current flowing through this circuit is VDD by R. So the current flowing through this resistor will be Vi plus VDD by R. So the voltage drop across this will be Vi plus VDD. So your output signal V naught will simply be equal to minus of Vi plus VDD. And the current, output current, will be minus of Vi plus VDD by R. So that's it. So I'll stop at this point, and then